Hello, I'm Yasir. Today, I will try to apply the fourth order Runge-Kutta method to the SIR model. So for doing that, I share the screen first. For doing that, I bring this model, the SIR model, from this website to the whole. When Runge-Kutta fourth order Runge-Kutta method is mentioned here, I will first compute K1, then K2, then K3, then K4. For all the consider because I consider the SIR model. So there are three equation in SIR model. One for susceptible, one for infected, and third one for recovered. And and these are the different stages for the Runge-Kutta method: K1, K2, K3, K4. So I apply the one stage for every equation, then second stage for all the three equation in SIR model, and then K3, K4, and after K4, I would find a solution at the next time. So I bring this formula for the indicator method of the table. And then I also bring this model, SIR model number. So I will solve every equation using. I will discretize every uh, all the equation using the fourth order Runge-Kutta. So I apply the first stage K1. So for K1, I say that's suppose that that's K11. K11 can be written as H, the step length, and then function of X naught Y naught. So this will be evaluated at minus beta I. Instead of I can use I as well. So I use N, IN, SN. I can use I as well. So yeah, this is for the making it generalize. So that will work for every grid point. So that's a general way to write to discretize these equations. Then I have the next for next equation it will be, I write it as K12. So K12 can be written as H and then beta IS. So beta IN, that's right, minus gamma plus gamma IN. And for the third equation, it would be K135 I believe. Yes. So that would be a H gamma IN. So I applied the first stage on all three equations. Now I will suppose that if it is a stage, so I will apply the second stage on all three. For second stage, I use the symbol notation with I use K21. K21 is for the first equation. When when second stage will be applied on the first equation of the SIR model, the first equation is minus beta I guess. H. So it says that y naught plus half K1. So this thing can be used for the independent variable if equation contains some independent variable x. So then this part will be used. If the equation does not contain any independent variables, here the independent variable is t. Only the derivative is there, but there is no term of containing independent variable. So I will just use this thing, the second component. So it is y naught. Y naught means that it's yeah, for susceptible, it would be a S naught. So it's a S naught. So what is S naught? So that would be a SN. So it's a SN. It's minus beta. And then for IN, it would be a IN plus half K1, K1, the infected one. And then S, then SN, also, the previous equation for susceptible is K11. So I use it as 1 over 2 K11. And now K22. K22 is H into beta IN. IN is IN plus half K12. And then SN plus half K11. And then minus gamma. Minus gamma. So for I, it would be IN plus 1 over 2 K1. Then K23. K23 would be H and then gamma and then IN plus half K1. And also, this is the first stage for three equations. This is the second stage for three equation. Now I will apply the third stage for three equation. Third stage is it says y naught is Sn, and then half, and then the k naught is the previous one, previous component. So I will use the third stage as write it as K31. When third stage will apply on the first equation. So it is H, then minus beta, and then it will be IN plus half K21. No, it would be not K, it would be K2. For IN it is K2. And then multiply by Sn plus half. That would be a K21. For susceptible, the previous equation was K21. And then I write K32. K32 is H into beta In plus half K22 then S in plus half K1 and gamma into In plus half K2. Third stage, third equation would be K33. So H gamma In plus half K. That was the third stage. Now I write the fourth stage. The fourth stage is without anyway, so it's just K3. Why not plus K3? So the third stage would be K41 In plus K32. Then Sn plus previous component for susceptible is K31. I write 31. And then K42. So that's H to beta. It's In plus K. Previous component for In is 3 H2. Then Sn plus previous component for susceptible is 3 K3 minus gamma into In plus K C2 very close. And then K43, that's H times gamma and In plus K32. So that's the fourth stage. No, I write this one. The final stage, the red can be written as Y. For first equation, it would be 1 over 6 K1, Y1. Instead of Y1, I use Yn plus 1. Yn plus 1 is equal to Yn, Yn plus 1 over 6 plus 1 by 6 K1. So here Y1 is N plus 1 and Y0 is N. And then 1 over 6 K1 plus 2 K1. K1 is just, I will not Yn, so I will write it as Sn. For first equation, I will write as Sn plus. This would be Sn. And that would be the K11 for susceptible plus 2k. The next one is k. No, look at it. The first one is k11, then k21. So k2, k3, k4. So it's a k21. K21 plus 2 times k31 plus k41. That's S for S and for I n plus 1. For I n plus 1. I n plus 1 is equal to I n plus 1 by 6. So here that would be a k21, then second stage for second equation. So k12, k12, k22, k1 plus 2 k22 plus 2 k32, then plus k42. Now for Rn plus 1, Rn plus 1 is equal to Rn plus 1 by 6 R12 plus 2 times R22. No, it's not R. K. So it's a K13 and plus 2 K. This is 2 2, so 2 1 2 2, and then this would be a 2 3 plus 2 K 3 1 3 2 and 3 3, then plus 4 1 4 2 4 3. So I wrote the equation. Now where I will construct the code in Matlab. So I will start with K11. Now the rest of the things would be the same as for Runge-Kutta 2. The rest of the thing is that CLC clear all, close all, and then the first then the time start at 0. So T not equal to 0. Then time ends at 100. So that's the final limit for time, and then it's a number of grid point are 150, and then the T variable, the independent variable on the x-axis. So that start from T naught and it's end at T1, and number of points will be 150. So it will divide the domain T naught to T1 into n plus 1 subintervals. And then dt is the time, it's a length, steps and step size. These are the values of the parameter beta and gamma. And then S is the dependent variable, I is the dependent variable, R is the dependent variable. And here, these are the initial condition. S1 is 1, I1 is 3, R1 is 0. So these are the initial condition. Now I will move the first stage of the Runge-Kutta method. The first stage would be I wrote it as what is that? So here, so first stage is K11, K11, K11 is dt and then minus beta I at I. So instead of I by u, n, n is equal to n. Then I have to use the n here. I n Sn and then beta I n So that would be the K12. That's K12. So it's beta into IN SN minus gamma IN. And then K13. So dt is the step size h, gamma is the parameter, and I. And next is K21. 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 dt minus beta in plus half K12 Sn plus half K11. Then the third stage, then second stage. It's the second stage applied to the for all three equations. So K2 and half. So the previous component of infected is K12. The previous component of S is K11. And then here is N. Previous component of infected is K1. And then K2, 2, 1, 2, 1, 2, 2, 2, 3. The gamma and then K1. Right. So it is easy to write this. I use the copy and paste because this is the easy way instead of writing the whole thing all the time. So yeah, instead of writing all new things, so I just make changes in the paste version. So that's a 3-1 not paste version percentage. For making the computation easy, I so susceptible that's uh, no, it's 2. And for susceptible it is 2-1. That's 2-1. That's 2-2. And this is 2-2. This is 2-2. Yeah, writing. So then, no, the fourth one, the third one, and then third, there is a fourth component. Fourth component is without the 0.5. The previous component. Previous component for infected is 3A3D. Then without 0.5, susceptible previous component is 3-1. And then here for IN is a K3, K3, and this would be the K for us, it would be a K3 then. And then for I taps a K3. Constitution will be found as Sn plus 1 is equal to Sn plus 1 by 6 K11 K11 plus 2 K31 plus 2 K31 plus K41. Then here plus 1 by 6 K12 plus 2 K22 plus 2 K32 plus K. K4 2, K3 2, K2 2, and K3 1 to 5. And then R8 1 by 6, K13 plus 2, K23 plus 2, K33 plus K2. So the last component, K4. So, and now I'll put the code and see what happens. So, this K4, there should be a 4 1, 4 2, 4 3. So that's error. It's I will not say error because the exact solution is not available. If I have an exact solution, then you can say that can be error because. But now I compared the solution with the OD45 solution. The OD45 is a Matlab solver that can be used to solve initial value problem, and this Runge-Kutta method can also be used for initial value problem. So that's why your model is the initial value problem. So that's why, so it can be solved with the Runge-Kutta method of either 2 or 4. So here this is the error. So that was the Runge-Kutta 4. Runge-Kutta fourth order mean that it's a accurate fourth order. It gives the fourth order accuracy. So that's why it is called fourth order Runge-Kutta fourth order Runge-Kutta method. So and this thing, the other solution is obtained using OT45 solver. Now I end this video. Bye.